Section 13.10 is all about oxidations. Oxidation can be very simply defined as the addition of oxygen or the removal of hydrogen. When we oxidize alcohols, we're mostly going to be talking about the removal of hydrogen. So, for example, if we have two propanol and we do an oxidation, we just use brackets and we write a capital O in there. That just stands for oxidation. And if we remove these two hydrogens from the molecule, we form a ketone in this case, and that's going to be acetone, okay? So that's a very typical type of thing, all right? That's going to be an oxidation reaction, okay? Now, a primary alcohol can be oxidized. Okay, again, we'll remove two of these hydrogens, and that will make an aldehyde. Okay, aldehydes can be further oxidized to form carboxylic acids. Okay, so let's analyze carefully what's going on here. When in this first example here, we are removing hydrogen, okay? So that's called an oxidation. In this second example, in this first step, we're removing hydrogen. So that's what I loosely define as being an oxidation. In this second step, as we go from our aldehyde to a carboxylic acid, we're adding an extra oxygen atom in there. So that's defined as oxidation. Okay, so those are just some kind of bits and pieces of basic definitions of what an oxidation reaction is. If you go from an alcohol to a ketone, if you go from an alcohol to an aldehyde, if you go from an alcohol to a carboxylic acid, those are all examples of oxidation. Okay? Now, there's a bazillion different kinds of oxidizing agents. The simplest ones from bleach on up to these fancy chromium and Martin reagents and things like that, okay? So let's talk about the oxidation of primary alcohols. All right, and there's two reagents you want to learn for this. One of these is called the Jones reaction, okay? If you're taking my class, you can just write Jones above an arrow there. If you look at it in the book, it's chromic acid and sulfuric acid. There's different ways of writing this. That's sodium dichromate, sulfuric acid, water, and there's also some acetone in there to help dissolve the organic compound you're trying to oxidize. Now, what you form from this Jones reaction is a carboxylic acid. Okay? So remember again, we're doing two things. We're removing hydrogen from the molecule, and we're adding an extra oxygen atom to this molecule. So those two indicators tell you that we are oxidizing that primary alcohol to a carboxylic acid. Okay, so we're literally taking away those two hydrogens and adding a carbon-oxygen pi bond. And that's the Jones reaction. Okay. Now, some scientists, long time ago, decided, hey, how can we oxidize this only to the aldehyde? What if we wanted to get to the aldehyde and stop there? And there are different reagents that allow you to do this. One of which is pyridinium chlorochromate. Some textbooks teach you that it's because the chromium has a reduced reactivity because of the pyridine, but technically it's because there's no water employed in the reaction. Now, PCC stands for pyridinium chlorochromate. Okay? And look at the reaction conditions. We do this in an organic compound called methylene chloride. And from this chemical reaction, you isolate the aldehyde. Okay? So remember what we're doing there. We're taking away this hydrogen on the oxygen, and we're taking away only one of the hydrogens on this carbon atom. And so then you form a carbon-oxygen double bond between those two positions, okay? So we normally draw the double bond O always pointing up, so it might be confusing because the alcohol is pointing to the bottom right. And we always draw this aldehydic hydrogen, okay? We'll show why that is later on when we talk about aldehydes and stuff, okay? So that's primary alcohols, okay? So primary alcohols can form carboxylic acids with Jones or aldehydes with PCC. Okay? Now let's talk about the oxidation of secondary alcohols. Well, that's not a secondary alcohol. Now, if I treat this with Jones, that will oxidize that guy up to the ketone. Now, this ketone is not chiral. It's lost its stereogenic information when that carbon-oxygen bond gets converted to a carbon-oxygen pi bond, okay? Now, the reason why is because the alcohol is sp3 hybridized, the carbon there is tetrahedral, and the product ketone, it's flat, it's sp2 hybridized and planar. So that you lose the stereochemistry there. I just thought I would show that that there in case you were wondering, okay, or wanted to see some more intricate examples. You could also take this same molecule and treat it with PCC, and that's also going to oxidize the secondary alcohol to a ketone, okay, same thing. All right, so you have your choice. You have your choice. You can use Jones or PCC. Okay. So let's do some problems. Okay. Okay, let's try to do problem 13.22. It says predict the major organic product for each of the following reactions. So we basically just need to memorize what's going on there, okay? So PCC is the pyridinium chlorochromate. That's the more mild oxidizing agent that will selectively oxidize primary alcohols to aldehydes. Okay, so that alcohol out there is way away from that stereogenic center, is going to be the aldehyde. And what happens over here with this aldehyde? Well, remember, the whole purpose of the PCC is to oxidize the alcohol to the aldehyde and then stop there. So the aldehydes do not oxidize with PCC. In molecule B, we're treating this with Jones. And remember, Jones is a very harsh oxidizer. We've got sulfuric acid in there, which is, pretty strong acid. And we got sodium dichromate, which is a very toxic material. So just think strong, toxic, dangerous. So this is going to really go all the way and give you a carboxylic acid. Okay. In letter C, we're adding excess chromium trioxide and H3O+. That's the same thing as Jones, okay? This is a Jones oxidation. This is a Jones oxidation. Okay. You're just starting with different chemicals. So Jones oxidation, remember, oxidized alcohols all the way to the carboxylic acid because the intermediate aldehyde just keeps reacting. So that means we're going to need to react this aldehyde to form a carboxylic acid, and we're going to need to react this alcohol to a carboxylic acid as well. So in molecule C, we're going to be forming the carboxylic acid on the left-hand side of the molecule, and we're going to be forming a carboxylic acid on the right-hand side of the molecule. All right, in letter D, we've got this primary alcohol here and PCC, so that's going to oxidize that primary alcohol to the aldehyde, and you just kind of need to memorize those kind of transformations. Okay. In letter E, we've got a secondary alcohol. Secondary alcohols oxidize to the ketones using either method. Oh, so there it is again, right? So this, remember again, we call it Jones. So Jones or PCC are going to oxidize this cyclopentanol to cyclohexanone. Okay. Now please don't get confused about certain types of reactions. Let me give you some bonus material here. If you have something like this, okay, and you treat this with PCC, remember PCC will oxidize primary and secondary alcohols to aldehydes, okay? So we form the aldehyde from that primary alcohol. Now what happens to the other alcohol in this organic molecule? This carbon atom right here has no hydrogens attached to it to remove to make a carbon-oxygen pi bond. If you try to make the carbon-oxygen pi bond there, you're going to end up with 5 bonds, okay? And we do not want to draw carbon with 5 bonds ever in organic chemistry. So it turns out that that tertiary alcohol does not react, okay? So let's fix that. And we just want to leave it unreacted, okay? So tertiary alcohols do not react with PCC or Jones or any kind of ordinary reagents that we've so far discussed, all right?